Namaste. Welcome to the lecture series on basic thermodynamics. This is module 5, part 1, ideal gases, lecture number 10. Myself, Dr. nsatheeshkumar, Associate Professor of Mechanical Engineering, Canara Engineering College, Bantwal. So, we will continue with the numerical on gas mixtures. Two isothermally insulated vessels, each of 0.85 meter cube in volume, are isolated from each other by a partition wall. One of the vessels contains nitrogen and the other oxygen, each at 5 bar and 100 degrees Celsius. As soon as the partition between the vessels is removed, the gases mix adiabatically. Determine the increase in entropy of the gas mixture. So here there is a isothermally vessels are there, two vessels are there, each separated by a partition and each having a volume of 0.85 meter cube. One of the vessel contains nitrogen and other contains oxygen, both at 5 bar and 100 degrees Celsius. Now you have to remove the partition and the gases mix adiabatically, so you have to find out the increase in entropy of the gas mixture. So the pressure and temperature of the gases are equal. So that means even after mixing, the temperature and pressure will not change. That means the pressure remains as at 5 bar and temperature at 373 Kelvin, but the volume of the mixture will be 2 times the 0.85, that is 1.7 meter cube, and the pressure of N2 and O2, since whatever the mass of the N2 and O2, now it occupies double the volume, so its pressure has to reduce by half. That means Pn2 by P mixture is Vn2 by Vm, so 0.85 by 1.7 is 1 by 2. So Pn2 is 0.5 into 5, that is 2.5 bar, and PO2 is also 2.5 bar. That means the pressure reduces to half of the initial volume because it occupies double the volume. Now using perfect gas equation, the mass of nitrogen you can find out. So Mn2. So perfect gas equation, PV is equal to MRT you have to use, and after proper substitution you will get as mass of nitrogen as 3.84 kg and mass of oxygen as 4.39 kg. So calculation I leave it to you. You make proper substitution and find the answers. Therefore, the increase in entropy of the mixture, this is the formula for the increase in entropy of the mixture, mass of nitrogen into gas constant of nitrogen into Ln by N2. Similarly, for oxygen it is MO2 RO2 Ln by O2, so you have to add. So after proper substitution, right, so you will get it as 1.575 kilojoules per Kelvin. Now let us solve one more problem. 2 kg mole of CO2 at a pressure of 1.8 bar 80 degrees Celsius is mixed in a thermally insulated vessel with 3 kg mole of N2 at 2.2 bar 60 degrees Celsius. When the mixture is at equilibrium, determine the final temperature and pressure and the change in entropy of the mixture. Assume CvCO2 is 0.653 kilojoules per kg per Kelvin and CvN2 as 0.741 kilojoules per kg per Kelvin. So 2 kg mole of CO2, so that is what is given at a pressure of 1.8 bar and 80 degrees Celsius, is mixed isothermally, so there is no change in temperature, in an insulated vessel with 3 kg mole of N2 at 2.2 bar and 60 degrees Celsius. Okay, it is thermally insulated vessel, thermally insulated vessel. When the mixture is at equilibrium, determine the final temperature and pressure and also the change in entropy of the mixture. The specific heat at constant volume for CO2 and N2 are given. So we have the formula for the mean temperature after mixing. So NCO2, CvCO2, TCO2 plus NN2, CVN2, TN2 by Nm, that is mixture Cv for the mixture. Now the molar specific heats at a constant volume, the constant gases are, that is Cv bar, it is actually not Cv. Cv bar is a molar specific heat, so that can be found out into molecular weight of CO2 into Cv of CO2. So that can be obtained as 28.73 kilojoules per kg mole Kelvin for CO2, and CVN2 also can be found out by a similar formula MN2CVN2, and it is found to be 20.75 kilojoules per kg mole Kelvin. So this is how you would find out the molar specific heats at the constant volume for the given gases. Now, if you make the substitution for the formula for the equilibrium temperature after mixing, it is 342.6 Kelvin. Okay. Now the final pressure of the mixture Pm is equal to Nm R bar Tm by Vm, gas equation. So volume of the individual gases VCO2 is equal to NCO2 R bar TCO2 by PCO2. So if you make proper substitution there, so you will get it as 32.61 meter cube. Similarly, the volume of nitrogen is 37.75 meter cube. Okay, so all these things I am not giving any time for you to calculate, so you can go through the lecturing and later you can calculate. Okay, so total volume is VCO2 plus Vn2, so you will get it as 70.36 meter cube. Therefore the final pressure, now once again you have to use the final pressure formula, so you will get it as 2.02 bar. Now the partial pressure of the individual gases, so PCO2 is NCO2 by Nm into Pm, the familiar formula for all of you. So it is 0.808 bar, so Pn2 is 1.212 bar. Okay. Therefore, the entropy change of the mixture is given by delta S bar mixture is equal to delta S bar CO2 plus delta S bar N2. So here delta S bar CO2 and delta S bar N2 has to be calculated separately. Then you have to add. So delta S bar CO2 is NCO2 into Cp bar CO2 Ln Tm by TCO2 plus minus R bar Ln PCO2 at 2 divided by PCO2 at state 1. That means pressure of CO2 at state 2 divided by pressure of CO2 at state 1. Similarly, you can write the expression for the delta S bar of nitrogen as NN2 Cp bar N2 Ln Tm by Tn2 minus R bar Ln Pn2 at state 2 divided by Pn2 at state 1. So here, before you make the substitution, better you calculate Cp bar of CO2 using the formula R bar plus Cv bar CO2, and you get it as 37.04 kilojoules per kg mole Kelvin, and Cp bar N2 is R bar plus Cv bar N2, R bar plus Cv bar plus N2. Of substitution, you get it as 29.064 kilojoules per kg mole Kelvin. Now, after a proper substitution in the formula for delta S bar mixture, so you will get it as 28.45 kilojoules per Kelvin. So with this I conclude the part 1 of module 5, that is the ideal gases. With the next lecture I will come to you with the real gases. Okay, thank you.